Hello everyone, and welcome to this video on orthogonal matrices. So in this video I'll just introduce the concept of orthogonal matrices, define what is an orthogonal matrix. Then I'll go into several examples where we'll be given a square matrix and asked to determine whether or not that matrix is orthogonal. And throughout this procedure, throughout these examples, I'll also demonstrate to you some properties of orthogonal matrices. Alright. So first, what does it mean for a matrix to be an orthogonal matrix? So an orthogonal matrix, which is a matrix A that is, square, some n by n matrix with real entries. An orthogonal matrix A is a matrix whose inverse matrix is equal to the transpose matrix. So it's a matrix whose inverse is equal to its transpose. Right? Remember the transpose, you just switch rows with rows and column numbers. Right? So a way to verify this, is the inverse of the matrix equal to its transpose, is multiply the matrix by its transpose in either order, and you should get the identity matrix. Right, remember that's what it meant to be an inverse. Right? When you multiplied by an inverse in either order, you got the identity matrix back. So if the inverse of a matrix is its transpose, then if you multiply that matrix by its transpose on either side, you should get the identity matrix. Okay. So an orthogonal matrix is a matrix whose inverse is its transpose. Okay, and that's going to be these last lines here. That's the way I'm going to verify whether or not a matrix is orthogonal. I'm going to multiply it by its transpose and see if I get the identity matrix. And if I do, great, the matrix is orthogonal. And if I don't, great, the matrix is not orthogonal. All right, and then like I said, I'll also show you some properties, some things that'll show up often when you're looking at orthogonal matrices as we go through these examples. Okay, so in each of my examples, I have the same instructions. Okay, determine whether the matrix is orthogonal. So like I said, the thing I'm going to try to verify here is the transpose of the matrix its inverse. So I have a 2 by 2 matrix A here, 2 by 2, where the columns are the square root of 2 over 2, negative square root of 2 over 2, and then this column is the square root of 2 over 2, square root of 2 over 2. Alright, so let's see what is A transpose. Alright, the transpose is pretty easy to write, so it should be again another 2 by 2. So the first row of A becomes the first column of A transpose. So it'd be square root of 2 over 2, square root of 2 over 2, right, both positive. The first row of A becomes the first column of A transpose. And then the second row of A becomes the second column of A transpose. So that was negative square root of 2 over 2 and positive square root of 2 over 2. All right. So what I'm going to do now is multiply these. So what is A times its transpose? All right, so that would be, now something I'm going to do is I'm going to pull some scalars out here. I notice every single one of these has the square root of 2 over 2 in common, so I'm going to pull that out. So it's the square root of 2 times, square root of 2 over 2 times the matrix 1, 1, negative 1, 1. Right, there's matrix A. Multiplied by, and again these all have the square root of 2 over 2 in common, so square root of 2 over 2 pulled out, times the transpose 1, negative 1, and then 1, 1. Right. And that's the transpose of this matrix. Right. Now you can move scalars around, remember? So I can multiply these two scalars. So square root 2 over 2 times square root 2 over 2, that'd be 2/4 or a half. And then I'm multiplying these matrices here, right? So a 2 by 2 times a 2 by 2 equals, just multiplying these two here, I get 1 plus 1, right? Just 2. Then negative 1 plus 1, 0. Then negative 1 plus 1, 0 again. And positive 1 plus positive 1, positive 2. And putting that half inside, I do indeed get the 2 by 2 identity matrix. Alright, and you can verify the other way too, but like if you just show one of these, that's going to be good enough. So this is showing me that A transpose is A inverse. Alright, because when I multiply them, I get the identity matrix. And if that's the case, if a matrix's inverse is equal to its transpose, then that matrix is what they call an orthogonal matrix. Okay, so pretty easy to verify. Just multiply a matrix and its transpose. Alright, now let me point some things out. Alright, let me point some things out. One, not only would A be orthogonal, but A transpose would also be orthogonal. Right? If A is orthogonal, A transpose is going to be orthogonal too. Because, if you take A transpose times its transpose, well, the transpose of A transpose is A. So if you multiply A transpose and A transpose transpose, which is just A, you're getting the identity matrix. So that's something I'll point out. Right? If A is orthogonal, then A transpose, or in this case, because A is orthogonal, A transpose is A inverse. This is also orthogonal. All right, again, that's because of this, right? Since A transpose multiplied by A transpose transpose would be equal to the identity, right? Because again, this is just A transpose times A. All right, would be the identity. Okay. So that's one thing I want to point out. Another thing, let's find the determinant of A. Now it's just a simple 2 by 2 matrix, right? So easy to take the determinant. What's the determinant of A? Well, it's just a 2 by 2, so it would be the square root of 2 over 2 squared, right, times itself, and then plus that again, right? Because it'd be minus the product of this diagonal. So then that'd be again the square root of 2 over 2 squared, right? This times this minus this times this, but there's a negative there, so it's going to be plus. Well, this is a half plus a half. That's 1. I'm going to point something out here that you'll see in another example later. Any orthogonal matrix is going to have a determinant of either 1 or negative 1. Any orthogonal matrix is going to have a determinant of 1 or negative 1. All right, now be careful. This does not mean that if a matrix has a determinant of 1 or -1 that it's orthogonal. All right, the other way around is not true. But if a matrix is orthogonal, then its determinant will be 1 or -1. And this tells us something else too. This tells us something very important about linear transformations. So this tells us that, if A is an orthogonal standard matrix for some transformation, is an orthogonal standard matrix for some linear transformation, or a linear operator for, because it's a square matrix. Say T from, say, Rn to Rn, then that transformation is what they call an isometry, meaning it'll preserve angles and norms. It'll preserve the angles between vectors, and it'll preserve the lengths of vectors. All right, so it'll just take a picture from the original and send it to, just a rotated or a reflected picture in the other space. Then transformation T is what they call an isometry. All right, so like, I'll say norms and angles are preserved. All right, let me show you what I mean by this. It's just going to basically take the standard, it takes the standard basis vectors and just rotates them or reflects them. That's it. They don't change the length of the vectors. They just change where they're situated, how they're oriented, possibly. So let's take a look here. All right, let me go to I'll go to my picture, and I'm going to call these columns. I'm going to call these columns of A certain vectors. Right? So let's say this is vector, v1, and this is vector v2. Okay, vector 1 and vector 2, the square root of 2 over 2, negative square root of 2 over 2, and square root of 2 over 2, square root of 2 over 2. All right. So if this is a matrix, the standard matrix for some transformation, then these vectors are what the standard basis vectors would go to. All right, so if you go back, here's a GeoGebra. So what I have here in R2, these are the standard basis vectors, right? My vector here is 1, 0. And my other vector, maybe I should call those vectors on the page something else. Maybe, how about U1 and U2, because I've got V1 and V2 already written in the website. So let's say vector U1 is this first column vector of A, and vector U2 is the second column vector of A. All right, so here, vector 1, 0, and the vector 0, 1. Now let me put in those column vectors. Those column vectors are where the original standard basis vectors would map to if our matrix was the standard matrix for some linear transformation from R2 to R2. All right, so 1, 0, right, 1, 0 would map to the vector square root of 2 over 2, negative square root of 2 over 2. So let me put that in. Let me call that again U1. All right, equals, and that's square root of 2 divided by 2 times the vector 1, negative 1. All right. And again, I'll make this also a red vector, because that's where the first standard basis vector is going, and 1, 0 is in red. I'll have this be in red as well. All right. And the same thing for U2. All right, U2 is my second column here. That'll be what that'll be the vector 0, 1 from the standard basis will map to this vector. root 2 over 2, root 2 over 2. So I put that in. Here's u2. Vector u2 is the square root of 2 divided by 2 times the vector 1, 1. And again, the vector 0, 1 was in green. This is where it's going to map to, so I'll also color this in green. And do you see how the lengths of the vectors weren't changed and the angles between them weren't changed? Right? You know, vector 1, 0 and 0, 1 are orthogonal, right? Under the dot product, they form a 90-degree angle. And these vectors are also orthogonal, right? V1 maps to U1, V2 maps to U2. In fact, they all kind of are on, they're pointing to the, points on the unit circle, right? Here's the unit circle. So you see how my original standard basis just rotated a bit, right? The lengths of the vectors were preserved and the angle between the vectors are preserved. And that would be the case for any pairs of vectors. The lengths of the vectors would be preserved under this transformation, and the angles between them would be preserved. All right, so that's something. That's another thing about orthogonal matrices. Orthogonal matrices represent an isometry. They represent a transformation where it's just taking vectors and just simply rotating them a certain amount, or flipping them over. Right? You could do a reflection as well, but not actually changing the shape. Not actually changing the angles or the lengths of the angles between the vectors or the lengths of the vectors. All right, so again, some nice things about orthogonal matrices. If a matrix is orthogonal, its transpose or its inverse will also be orthogonal. Its determinant will be either 1 or -1, right? And it's only going to be -1 when the orientation of the vectors flips, or when you get a reflection in your transformations. And now let's take a look too at these columns. All right. So look at the columns. The set with the u1 and u2, the set with the the first column vector, square root of 2 over 2, negative square root of 2 over 2, and the second column vector, square root of 2 over 2 and square root of 2 over 2. I mean, you noticed how, again, back in my picture, those were these vectors here, right? These two. See how they're both a unit long. They both point to a point on this unit circle. And they're orthogonal. Well, what kind of a set did you call that, right? When you had vectors that were orthogonal to one another and also all unit vectors, that was an orthonormal set. All right. Again, this is an orthonormal set. In fact, it's an orthonormal basis for R2. Remember, orthonormal, under the dot product, right? I'll say under the dot product, the standard inner product here. Okay. So if you took the dot product of these two, you'd get 0. Right? You'd get a half minus a half. That's 0. And they each have a unit of length, right? If you did the norm, if you did the dot product of each vector with itself, you'd get a half plus a half. You'd get this. You'd get 1 for each one of these. So they're orthogonal vectors that are also unit vectors. So an orthonormal set. And that is going to happen with the columns and the rows. Right? Because remember, the rows of a matrix are just the columns of the transpose, and the transpose is also orthogonal. All right, so the columns of an orthogonal matrix will form an orthonormal set. The rows of an orthogonal matrix will form an orthonormal set. All right. All right. And if one of these things doesn't happen, then you don't have an orthogonal matrix, right? If the columns do not form an orthonormal set, then the matrix is not orthogonal. If the determinant of the matrix is not 1 or -1, then the matrix is not orthogonal. If the transpose isn't the inverse, right? If the inverse isn't orthogonal, then the original matrix isn't orthogonal as well. All right, now I'll point these three things out with each example as we go through. All right, so that first example was a 2 by 2 matrix that was orthogonal. Right? Its transpose was its inverse. All right, so here's another one. So I've got another 2 by 2 matrix. First column 4/9, 4/9. Second column -4/9 and 3/9. Now I know 3/9 is 1/3, but I just wanted to write it so they all have the same denominator here. And the question is again, is this matrix orthogonal? Is this an orthogonal matrix? So again, very easy to verify. Just look at the transpose. That'd be first row of A is the first column of A transpose, so 4/9, -4/9. And the second row of A is the second column of A transpose, 4/9 and 3/9. All right, and then let's multiply them and see if we get the identity matrix back. All right, so what is the product? Again, you can do A times A transpose times A, right? If they're truly inverses, it won't matter what order you put them in, you'll get the identity matrix back. Right? So I'll do it the same order I did last time, A times A transpose. Now this, just like last time, I'll pull some scalars out. So matrix A here, they all have a 1/9 in common, so that's 1/9 times the matrix 4, -4, 4, 3, right? Times, and then same thing for A transpose. Each of those has a 9th in common, and then that's times the matrix 4, 4, -4, 3. And moving the scalars out front, you get 1/81st, and then the product of the two matrices, right, the product of these two matrices, this and this, will go here. First row, first column would be 16 plus 16. That's 32. And really I can stop. Because look, when I multiply by 1/81st, that's not going to be 1 in the upper left corner. This is not going to be the identity matrix, but I'll finish it off, right? So then we'd have, 16 minus 12, that's 4. So, that's not 0. So definitely not going to be the identity matrix. Then, 16 minus 12, again 4. And then 16 plus 9, 25, but this is definitely not the identity matrix. All right, so that means that A transpose is not the inverse of A. All right, and if that's the case, that means that A is not an orthogonal matrix. Again, very easy to verify. Just multiply a matrix by its transpose and see if you get the identity back. All right, now another way I could have told you that this was not an orthogonal matrix. Look at the column vectors. Again, say I call this vector u1 and this vector u2. What's the dot product of u1 and u2? Right. What's the dot product of u1 with u2? Well, that would be 4/9 times -4/9, that'd be -16/81, plus, and then 4/9 times 3/9 would be 12/81. Putting these together, this is not 0. This is -4/81. This is not 0. That means that the columns do not form an orthonormal set. They're not even an orthogonal set. Right? So the columns of A do not form, an orthonormal basis for R2, or I'll just say an orthonormal set, right, where each pair of vectors is orthogonal and every vector is a unit vector. So that means that's another way I could have said matrix A is not an orthogonal matrix. Right, you don't have to show both of these, right? This way is fine. What I just showed here, that A times A transpose is not the identity, but this way would also be fine if you show that the columns or the rows of the matrix do not form an orthonormal set, or an orthonormal basis for R2. Here it's R2 because it's a 2 by 2 matrix. So A is not an orthogonal matrix. All right. Another way I could have shown, right, so again this is another way I could have shown you that this was not orthogonal. I could have said, let's look at the determinant. If the determinant is something other than, if the determinant is 1 or -1, then it might be orthogonal, or you can't say anything. But if the determinant is not 1 and not -1, then you can say for certain that the matrix is not orthogonal. So what's the determinant of matrix A? Right, so again, it's a nice 2 by 2. All right. So that's 4/9 times 3/9. That's 12/81. And then plus, because it'd be minus, minus a negative here, right? Minus -4/9 times 4/9, so plus 16/81. And putting these together, it's going to be 28/81. This is not 1 or -1. All right. Now, if it were, like I said, if it were 1 or -1, then you can't really say anything. You have to check something else, because a matrix can have a determinant of 1 but still not be orthogonal, and I'll show you an example of that later. But if the determinant of the matrix is not 1 or -1, like this is here, 28/81, then without a doubt, the matrix is not orthogonal. Is not an orthogonal matrix. I'll just say A is not orthogonal. Okay, so yeah, lots of things that you can show there. To say that again, if the columns or the rows do not form an orthonormal basis for Rn, right, whatever n is, or R2 by, if it's a 2 by 2, it's R2. If it's a 3 by 3, it's R3, and so on. If the columns or rows do not form an orthonormal set or an orthonormal basis for Rn, it's not an orthogonal matrix. If the determinant of the matrix is not 1 or -1, it's not an orthogonal matrix. If the product of a matrix and its transpose is not the identity matrix, then it's not an orthogonal matrix, right? So lots of ways to show that it's not an orthogonal matrix. All right, so now I'm going to bump it up into 3 by 3s. Right. Oh, you know what? I forgot I wanted to show you a picture. Right, so again, here was our matrix again, sorry. We go back to the GeoGebra site. All right, and here was our standard basis vectors. All right, 1, 0 and 0, 1. If it was an orthogonal matrix, then the transformation that it corresponds to, right? If the transformation from R2 to R2 that it would be a standard matrix for should just rotate or reflect these standard basis vectors, right? It shouldn't change their length. It shouldn't change how the angle between them, right? If it were an orthogonal matrix, the angle between red and green would be the same, and the lengths of red and green, or the norms, would be the same. All right, let's see that that does not happen here. All right, so let's get rid of these. All right, so for this matrix, Remember, u1 is the vector 4/9, 4/9, 4/9, 4/9, and this is the this is the where the vector 1, 0 would map to under a transformation that's represented by this matrix. So I've got u1 equals 4/9 times the vector 1, 1. And look at that. You see how the length is definitely not preserved? All right, let me change that to red because this is where the vector 1, 0 is being mapped to by a transformation represented by this matrix. So v1 would map to u1, and you can see right away the length is not preserved. Right? It's actually shorter than a unit. And then putting in the other one, right, u2 was the second column of matrix A, as negative 4/9, 3/9, or negative 4/9 and then a third. Right. And then make this green, because it's where the green vector is mapping to. All right, and let me get rid. You see that so v2, right, the 0, 1 would map to this negative 4/9, 3/9, and you see again the length is not preserved, and the angles aren't preserved either. Right, if I get rid of these, the angle between 1, 0 and 0, 1 is 90 degrees. The angle between these two vectors is actually a little more than 90 degrees. All right, it's hard to tell maybe, but that's actually a little more than 90 degrees. So, and you could tell by if you did the dot product of these two vectors, you'd get a negative number, not 0. So they're not perpendicular, not orthogonal under the dot product. So lengths aren't preserved, and angles between vectors aren't preserved. This is not the transformation that this matrix corresponds to, that this matrix represents, is not what they call an isometry. Right? It doesn't. This matrix wouldn't represent an isometry. So even that's another way I can say, hey, this is not an orthogonal matrix. An orthogonal matrix would preserve angles between vectors and preserve lengths of those vectors' norms. All right. So now I'm going to go into our a 3x3 matrix. 3x3 matrix. Okay. So again, the question is this matrix orthogonal? Is it orthogonal? All right. So again, the quick easy check here. Now you could check, which I'll do in a minute. Are the columns an orthonormal basis for R3? Orthonormal basis for R3. If I looked at a transformation here, would this be representing an isometry? Take the 3 standard basis vectors to 3 other vectors that are also an orthonormal basis. What's the determinant of this matrix? Now again, if the determinant's 1 or negative 1, that doesn't mean anything. But if the determinant's not 1 or negative 1, right, then it's not an orthogonal matrix. Well, let's do the easy one first. Right? Just look at the transpose. So first column would be 2/3, negative 2/3, 1/3. Second column would be 2/3, 1/3, negative 2/3. And the third column, 1/3, 2/3, 2/3. All right, well, let's multiply these. So again, what's the product of A and A transpose? And just like with the last ones, I noticed all these have a third in common. So A is a third times the matrix 2, negative 2, 1, 2, 1, negative 2, 1, 2, 2. There's A times, and then again, same thing with A transpose. That they have a third as a common scalar to all those entries. So I'll pull that out. Times, and then 2, 2, 2, 1, negative 2, 1, 2, and 1, negative 2, 2. All right, so pulling the scalars out front, that's a 9th, and then I multiply the two 3x3 matrices. Right, and multiplying the, doing the first row, first column here, I'd get 4 plus 4 plus 1, that's 9. Then, 4 minus 2 minus 2, that's 0. And I'm hoping you're seeing, and you can verify this yourself, that you get 900090009 multiplying by 1/9. This is indeed the identity matrix, right? Put the 1/9 in there, you'd have 1, 1, 1 down the main diagonal and zeros everywhere else. So, this is telling me that A transpose is A inverse. So the definition holds. This is an orthogonal matrix, right? So the transpose of A is the inverse of A. Therefore, matrix A there is an orthogonal matrix. Okay. And if A is orthogonal, A transpose would also be orthogonal, right? A inverse would also be orthogonal. They're the same thing. All right. Now again, let's look at some stuff. All right. Let me verify some things. Now, remember I said earlier, since this is an orthogonal matrix, its determinant should be 1 or -1. All right. Let's see. So what's the determinant of A? Well, I'm just going to do some cofactor expansion down the first row. All right, so we'd have 2/3 times the determinant of 1/3, -2/3, 2/3, 2/3. Then plus -2/3 times its cofactor, but its cofactor would be the opposite of the minor, so it's going to be plus 2/3 then, right? Times the minor, 2/3, 1/3, -2/3, 2/3, and finally plus 1/3 times the minor, 2/3, 1/3, 1/3, and 2/3. All right. So this is 2/3 times, no, let's see, this would be 2/9 plus 4/9. So 6/9 or 2/3 again, plus 2/3 times 4/9 plus 2/9 would be 6/9 or 2/3 again, plus, and then 1/3 times, and then 4/9 minus 1/9 would be 3/9 or 1/3. And this is 4/9 plus 4/9 plus 1/9. That's 1. Now again, the determinant could be -1 as well. All I would need to do would be switch a column, and I'd get a matrix with a determinant that would be -1, or switch a row, and get another orthogonal matrix that would also have a determinant of -1. Right, so this worked out, right? I have an orthogonal matrix, and its determinant is 1 or -1. In this case, it's 1 again. If you look at the columns, again, I'll call this first column vector u1, second column vector u2, third column vector u3. If you look at the columns, right, look at u1 dot u2, it's going to be 0. All right. Take the dot product of u1 with u2, it is 0, and you can double check that. Take the dot product of u1 with u3, it's 0. And take the dot product of u2 with u3, it's 0. Right? And the norm of every single one of these vectors, the dot product of every vector with itself is 1. Would be this guy here. And the norm of every vector, which again you can verify for yourself, is 1. So the columns do form an orthonormal basis for R3. Orthonormal, right? Not just orthogonal, But all the vectors also have a norm of 1 under the dot product. Right? So that means that and if this is the case, then A is an orthogonal vector, an orthogonal matrix. Right? If this is the case, A is orthogonal. Right? Not this though. Right? Remember I said a determinant of 1 or -1 does not mean that the matrix is orthogonal. Right? Just be careful with that. And again, I'll show you an example when we're finally done with everything. And let me show you a picture. Let's go a picture. Let me draw these vectors in on the 3D calculator in GeoGebra. All right, so here's now this is, I've got it zoomed in a bit, and you can see the red. Actually, go to the website. So you can see the red vector is 1, 0, 0. The green vector is 0, 1, 0, and the blue vector is 0, 0, 1. Right, those are the standard basis vectors of R3, and they're orthonormal. Right, they're all 1 unit long, and the angles between any pair of them is 90 degrees. Right? And here's the unit sphere, right? The sphere centered at the origin. Notice how these just go to some point on that sphere. Right? These three vectors will point to some point on this unit sphere. Right? So you can see the red vector pointing to the blue vector and the green vector and all that. Right? All right. So I'll get rid of the sphere for right now. And let me put in those columns of A. Right, I'm going to put in those columns of A. So U1 was the vector, 2/3, 2/3, 1/3. So 1/3 times the vector 2, 2, 1. All right, and again, I'm going to color this. This is what the red vector, this is what 1, 0, 0 would map to in a transformation represented by this matrix. So I'm going to color this red. Right, so it's where the red vector would map to. Alright, so it's going from here to pointing here. Alright, then U2, the second column of matrix A was, -2/3, 1/3, 2/3. So that's 1/3 times the vector -2, 1, 2. Alright, and again, I'll color this blue because this is where the vector, green. This is where 0, 1, 0 would map. So I'm going to color this green. This is where the green vector would map to. So the red maps here. 0, 1, 0 maps there. So red maps to red, green maps to green, and then blue, the blue vector 0, 0, 1 from the standard basis would map to vector U3, which was 1/3, -2/3, 2/3. So that's 1/3 times the vector 1, -2, 2. And again, I'll color this blue because that's where the blue vector maps to. And what you're going to see is that these three vectors, right, red mapping to red, green mapping to green, blue. If I get rid of these, right, remember all these three point to some point on the sphere, right, on the unit sphere, every single one of these, and they form 90-degree angles with each other, the red and the green and the blue, and the red and the blue. Well, take these away, and we'll see that the three vectors they map to, red, green, blue, maybe I'll lighten up this color here, the color of the sphere, like a light green or something, or like this pale yellow. Oh, that was the vector. I did the vector. Oops. Sorry. Red. And then for the sphere, let's go like this pale yellow. Alright. But do you see that if I move this around a bit, you see these three vectors form 90-degree angles with each other? And also point to points on this unit sphere. Alright, just like the the standard basis vectors. All right, just like the standard basis vectors. So all these three vectors are just a rotation of the standard basis vectors. I just rotated them around and moved them to some other location, but they still have the same length. All of them are unit length. Right? They point to some point on the unit sphere. And they also have the same angles between them. Right? They're all orthogonal. Right? So a transformation represented by this matrix is an isometry, meaning that this would be an orthogonal matrix. Right? Again, angles are preserved, lengths are preserved. Right? Wonderful. All right, so I've just got one more 3x3 matrix, and then I'll list the properties that I've named so far at the end. All right, so one more example here. Got a 3x3 matrix. Now you can probably already tell that this is not an orthogonal matrix. Because look, if I called the first column, U1, the second column U2, and the third column U3, now the dot products would all be 0. If you did the dot product of U1 with U2, you'd get 0. If you did the dot product of U1 with U3, you'd get 0, right? Negative 12 plus 12. And if you did the dot product of U2 with U3, you'd also get 0. So these form an orthogonal set, but they're not orthonormal, right? The norm of U1, right? The norm of U1 would be 5, not 1. It would be the square root of 16 plus 0 plus 9, right? Square root of 25. This is not 1, meaning that the columns do not form an orthonormal set. They're an orthogonal set, but they're not orthonormal, right? They don't all have a length of 1 under the dot product. Columns do not form an orthonormal basis. They form an orthogonal basis for R3, but not orthonormal. Basis for R3, and if that is the case, then A is not an orthogonal matrix. And I could stop there. All right, that's all I needed to show. But again, let's verify it the other way, right? Let's see what A times its transpose is, right? And see if that's the identity matrix, because remember, an orthogonal matrix is a matrix whose inverse is its transpose. So what's the transpose? It'd be negative 4, 0, 3. 0, 1, 0. In fact, look, this is what they call a symmetric matrix. Right, 3, 0, 4. Right, do you see that A and A transpose are the same? And that means that they call that a symmetric matrix. A is a symmetric matrix. A symmetric matrix is simply a matrix that is the same as its own transpose. All right, but that doesn't mean it's orthogonal. Right? Doesn't mean it's orthogonal. Now multiplying these, hopefully you could see right away that A times A transpose is not the identity. Right, if I multiply this by this, the first row, first column would be 25. Right, I'd have negative 403 dotted with in the dot product with negative 403. The first row, first column would be 25, not 1. So right away I'm seeing that the A times A transpose is not the identity. So again, that leads me to the conclusion that matrix A is not one of these orthogonal matrices. Right? Its inverse is not its transpose. All right. And And then also you could probably verify that taking the determinant of this matrix would be negative 25. So the determinant's not 1 or negative 1. All right, I'll write that here. And if you want to verify this for yourself, all you do is a simple cofactor expansion down the second row or the second column. It would just be 1 times the determinant of the matrix with negative 4, 3, and 3, 4 as columns. The determinant of A is negative 25, which is not 1 or negative 1. So again, I can conclude that A must not be an orthogonal matrix. Right. And if I were to graph these vectors, negative 4, 0, 3, 0, 1, 0, 3, 0, 4, they'd be orthogonal, but they wouldn't touch the unit sphere. The lengths would change. All right, let me put those in actually. All right, let me get rid of these guys. So again, here are the standard basis vectors, right? 1, 0, 0, 0, 1, 0, 0, 0, 1. You see how they're all a unit length, so they're all touching a point on this unit sphere that I've got here, right? The unit sphere. If I put in the columns, again, the vector 1, 0, 0, if this matrix represented a transformation, the vector 1, 0, 0 would map to the vector negative 4, 0, 3, right? The first column, U1 equals negative 4, 0, 3, which you can clearly see has a different length than the red vector 1, 0, 0. So lengths are not preserved under this transformation, the transformation that's represented by this matrix. So the matrix is not in isometry. I could stop there. All right, again, I could stop there and say this matrix does not represent a transformation that is in isometry. It doesn't preserve lengths. Now it would preserve angles, but not lengths, right? Again, these are orthogonal. All right, you could take the dot product of any pair of these. It's equal to 0. So the angles would be preserved, but not the lengths, not the norms. All right. So again, we could say that this matrix is not an orthogonal matrix. It does not represent an isometry. All right. So after all this, I'm hoping you got some properties down. Hopefully, I've demonstrated enough to you where you believe these statements. All right. So here are some important properties of orthogonal matrices. So number 1. As we saw in the first example, right? First and third examples had orthogonal matrices. If A is an orthogonal matrix, then A inverse, or A transpose, is also orthogonal. And we saw that. Okay. Number 2. If A is an orthogonal matrix, then the determinant of A is either 1 or negative 1. So like I said, you gotta be careful with this one. Just because a matrix has a determinant of 1 doesn't mean it's orthogonal. Alright, so let me show you here. Be careful. Be careful. Here's a matrix. I'll do this, just do a 2 by 2. Here's a matrix with a determinant of negative 1. 4, 3, 13, 1. There. The determinant of this matrix is negative 1. All right, it's 12 minus 13. But A is not an orthogonal matrix. All right, I'm hoping you see this because look, the columns are not unit vectors, right? In fact, they're not even orthogonal. If I took 4, 1, if I did the dot product of 4, 1 with 13, 3, this would be 4 times 13, be 52 plus 3, that'd be 55. That's not 0. So the columns don't form, right? The columns do not form an orthonormal basis for R2. They don't form an orthonormal basis for R2, right? So again, I can say that A is not orthogonal. So just because the determinant of a matrix is 1 or -1 does not mean it's orthogonal, right? So be careful with that. But if you know your matrix is orthogonal, then the determinant will be 1 or -1. And then you could do what's called the contrapositive of this. If the determinant is neither 1 nor -1, right? If it's neither one of them, like if the determinant of a matrix is 10 or 7, or we saw earlier some matrices with determinants that are -25, like the last example. If the determinant is not 1 or not -1, or not -1, then you know for a fact that A is not orthogonal. All right, then here's one that goes both directions. Right, this is one we've seen as well. This is the best one. I think this is the best one here. I put some stars around it. It's important. Again, A is a square matrix, right? Some n by n matrix. A is orthogonal if and only if, right? So this goes in both directions. The columns of A form an orthonormal basis of Rn. Right. So as we in the rows also, right? But we can just look at the columns because again, the columns of one matrix are just the rows of the transpose and so on. And the transpose would also be orthogonal, right? So yeah, so you can so this gives me a couple ways to check if a matrix is orthogonal. One, I can multiply the matrix and its transpose, see if I get the identity, right? Because again, that was how orthogonal matrices are defined. An orthogonal matrix is a matrix whose inverse is its transpose. Or I could look at the columns of the matrix and see if they form an orthonormal basis of Rn. Right? Is every pair of them orthogonal? And are they all unit vectors? And this is going to be under the dot product, right? The standard inner product. Great. And if they don't, then the matrix is not orthogonal. Its inverse would not be its transpose. If they do form an orthonormal basis, then the matrix will be orthogonal and the inverse will be its transpose. Okay. All right, so very important these here. They just, again, remember the definition, or if you were to take away anything from this, remember the definition of an orthogonal matrix, a matrix whose inverse is its transpose. And then these three properties, right? If a matrix is orthogonal, its transpose or its inverse will also be orthogonal. If a matrix is orthogonal, then its determinant will either be 1 or -1. And if you do the contrapositive of that, if the determinant of a matrix is neither 1 nor -1, then the matrix will not be orthogonal. And finally, a matrix will be orthogonal if and only if the columns or rows of that matrix form an orthonormal basis of Rn. Great. All right, so I hope this was informative. I hope the examples made some sense. You could follow them. And I hope you enjoy practicing problems where you're dealing with orthogonal matrices. It's the only way to get better at anything is to practice, right? All right. Thank you very much for watching.